All right. A note on last week. The written assignment, remember, sometimes you'll submit stuff in My Open Math, like words that you type. Computers can't grade that. So those usually a 0 until I go in and read them. And so I am waiting till later today to grade those because a few people haven't turned in their finance written assignment. So if you need any help with that, let me know. I'm free after class if you need any tips. It's much like the homework questions that you did, except they're all connected. It's all the same problem, kind of like when we were playing around with Pete's house the other day in class. So it's a lot like that problem. Each part leads to another part, leads to another part. So you need to check as you go on that one. All right, so Math 105. This week, we have two things going on. Midterm exam needs to be taken one day this week. Whenever you're ready, let me know. And either I'll give it to you or set you up at a testing center. And then otherwise, we are doing statistics in class. And so this is actually a 2-week section. Part 1 is on data collecting with statistics. Part 2 is on analyzing stuff with statistics, although we'll do a little analysis in the collecting data part because we have to describe some of the data that we're working with. So let's get started. Oops, and someday I gotta figure out how to fix this thing so my pens show up when I need them. All right, so just some vocabulary and then we'll actually get in and do some statistics. Statistics is just a study of numbers, patterns in numbers. The numbers we work with are usually called data. Data is some kind of collected information. Some people differentiate between data and information. So for example, the number 46 is a piece of data. But unless you say what it means, it's not information. I say 46, so what? 46. But if I say, hey, I'm 46 years old, now it's information because it has context. So information is data in context. Okay, so if we know something about the data. So not only can we manipulate numbers, we can then apply what we've done to them. The types of data that we work with are usually numbers. But it could be other qualities. So we could have qualitative information. So can somebody give me an example of some data I might collect that's not numerical? Like I can get somebody's age, right? That's numerical. I can get your height. That's numerical. I can take your blood pressure or your temperature. What other things information could I get from you that's important information, but it's not numerical? The blood type, yeah, A positive, O negative. Okay, so that's a good example. That's qualitative information. What else? Gender, yeah, male, female. Yeah, so there's lots of examples. Gender, blood type. How about eye color? Race, birthplace, country of origin. So there's tons of data that we can collect. We can do certain kinds of analysis on it, but not the same kind of analysis we do with numbers, right? So we're going to play around with different kinds of data and how we can analyze it. Okay? So sometimes the data will be numerical, which is also called quantitative. Sometimes it's qualitative. It's some aspect of a situation or a person that's not a number. So we have two different kinds of data that we'll mess with. When we mess with the data, we do a certain calculation. We end up with statistics. Statistics. So a statistic is a calculation based on data. So common statistics that we use are, for example, average. So we'll review average. Average is also called arithmetic mean. Another popular one would be median. Minimum. Maximum, and the list goes on. There's tons of different things. We can look at a set of numbers and say, this is a calculation we can do. Sometimes the calculation is as simple as putting them in order and picking the last one or the first one. Other times it's a little more complicated calculation, like average. Sometimes we look at percents. That's a common calculation based on some question about a data. So we're going to deal a lot with percents in this chapter, as we've done with most chapters. All right, so let's see, some other things. We have, when we're collecting data, we have samples versus populations. So a population could be, for example, BMCC students. Now, if I just say BMCC students, that's any student that attended BMCC ever. It's quite a large population. So sometimes we'll narrow populations down. So we might see BMCC students in fall of 2016. So then you all are part of that population. I'm part of that population. I'm taking a class right now. A sample could be something like the group of us working on Math 105 right now. Okay. So we have samples, we have populations. All right, so we're going to get into sampling methods in just a little bit. That stuff's kind of boring, so I'm going to skip it for now. Or maybe I'm not. Oh. I'm glad I looked at my notes. I was getting this week mixed up with next week. Okay. So we'll do more terminology in just a minute. I'm going to ask you a question. Let's see. I'm going to get the question right by looking at my data over here. Okay. So the question is, how many movies have you seen in the last month? Hmm? What do you mean, generally speaking? Ah, okay, so that's a good question. So there's different kinds of movies. Theater, oops, there we go, versus kind of at home. If you watch them at home, it might be on, like, say, a DVD or streaming. All right, let's do theater first. Let's see. In the last 30 days, I have seen 0 movies in the theater. So let's define month as the last 30 days, right? Because somebody might think, like if it's the beginning of the month, oh, in the last 3 days. So 30 days. Okay, Micaiah says 2. None. Probably 2. Ben, have you seen any movies in the theater in the last month? Uh-oh, did I forget to share my screen, Fen? That's awfully tiny.
Oh, actually, I can see it.
Oh, I wish you would have told me. I'm sorry about that. Share screen. There we go. That's better. How many movies have you seen in the last month, Fen?
Actually, I didn't.
Haven't seen any. So Fen's 0 there too. Okay. So then what about at home, which could be like DVD or streaming? Maybe it was at somebody else's house, but not at a theater. And then the other question is, like, I watch lots of things at home, but they usually aren't movies. There's some kind of show. So for movie, I mean some feature-length film, not like a 30 or 45-minute regularly broadcast show. So like if you're into Flash, not Flash, unless it was a movie Flash. I think I've watched, let's see, I rewatched Harry Potter recently, one of those. Maybe 2. I'm thinking it's more likely 1, but I'm probably forgetting 1. I'm going to put 2 movies outside of a theater this month. You watched a lot? Movies? Make a guess. You watch quite a bit of Netflix. Yeah, I unfortunately have Netflix and I have Amazon Prime, which means I have an awful lot of access to movies, but I don't watch them, unfortunately. You're going to say 7? Okay. Julia? 3 in the last 30 days. Ian, take a guess. 15? Yeah. Yeah. You watched. Okay. Yeah. Yeah, like my daughter watches a ton of YouTube, but they're not movies. But she watches the equivalent time of many movies on YouTube. So that's a whole different category. Fen, have you seen any movies at home recently? Last 30 days?
Yeah.
How many about? Make a guess.
Is it counted for lessons movie? That would be a lot. About 2 or something.
Probably 2. Okay. All right. So we've got some data here, and asking a question can be kind of tricky because you have to define each part of the question and make sure everyone understands it the same way the person who's asking or looking for the data. So for us, in order to get appropriate answers to this question, we had to redefine a couple of things, and we're carefully define. So we had to define, what do we mean exactly by movies? What's a month, right? Elaborate 30 days. We separated movies into theater versus at home, which could be DVD or streaming. So the point is, we want to get the same kind of answer from each person. Otherwise, it could mess up the results somehow. Okay. So this number, let's see. Is it important that somebody watched no movies? Yeah, that's significant, right? So some data, having the number 0 in there doesn't matter. Some data it does. Kind of depends. So let's see. Another question I could ask. What is your heart rate right now? So that's numerical, right? It's quantitative. How do we go about doing that? Count. So everyone find their pulse somewhere and start counting. How long shall we count for? Yeah, so heart rate is usually given in beats per minute, right? So I should elaborate on that in my question so it's clear. Oops, beats per minute. All right, so usually people do something like go 10 seconds multiply by 6, or go 15 seconds multiply by 4, or 20 seconds multiply by 3. So there's a clock behind us. Ben, I hope you have a clock somewhere if everybody could find their pulse rate. No pulse?
It's like I stopped breathing too. I'm like, why am I stopping? I won't have any pulse then.
Fen, you have any luck getting your pulse rate?
No.
Like 37.
37 beats per minute?
Yeah, because I gave up.
Okay.
I don't even know.
Are you watching a clock? Doesn't count if you're not watching a clock. Did you get one? Could be. If you're pretty athletic, 56 beats per minute is possible. Julia, any luck? 88? Okay. What'd you get? $45.
Because I'm unathletic. Woo!
So some interesting things about this question right here. Did you do it right? So if we really want to get the heart rate right, we should have somebody trained in measuring heart rates do it, preferably a machine, right? Because we have lots of machines that do that. And then you're self-reporting. So for example, I used to have a low heart rate, then I had some heart trouble, now I have a high heart rate. I'm not happy with my high heart rate, so I tend to underreport it. I want it to be lower, but it's not. Other people miscount, miss beats, multiply wrong. So sometimes if we're looking for a certain measurement, we should take it ourselves. I mean, whoever's asking the question should take it, okay? So here we have self-reporting going on. Yeah, so right, we're sitting in a class, so the circumstances in which it's collected is important too. So there's other information. That information is usually referred to as metadata. So it's data that is not directly related, but it's related, right? So that'd be some metadata we'd want to collect with this. Your age, do you exercise much? What does it mean to exercise much? Things like that. So the one problem here, we have self-reporting. What else? There could be errors in the calculation. All right, let's take a look at another question. This particular question isn't too much different than the movie data. I couldn't have a 0 in this data because that would mean somebody was dead, and then they can't respond. So we're not going to have a 0 heart rate. But these are whole numbers. Nobody's going to count a fraction of a beat in a minute, although machines can count that. Humans can't easily do that. But these answers are generally going to be whole number answers. Let's see. How about your height in inches? So what is your height in inches? So let's see. Does anyone remember off the top of their head their height? Yes, I'm about 5'8", so 5 times 12 is 60, so that means I would be about 68 inches. So I might say that. Ian, he says 69. Anybody else want a height? 5'5", so that would be 65 inches, 68 inches. Fan, you want to throw a height in here for us?
Yeah, wait. Oh, about 16. Oh, no. Oh, yeah, about 60.
60?
Mm-hmm.
Okay. Actually, if I whipped out a ruler, I would find that depending on the shoes, I might be like 68 and a half. And that half used to be important to me, right? Now I don't care. With younger kids, we might take it to a fraction of an inch. So some data could have other values like decimals going on in it, okay? And this is one where totally somebody might report 68 and a half inches or 3/4 or a quarter, a fraction of an inch. Okay. So all of these are in inches. So numerical data could have decimals in it, and depending on the type of data, it could have a lot or a few decimals, depending on what we're collecting. Suppose we wanted to know how thick a piece of paper was. So let's see, what if we look that up online? What might we find? Thickness of paper. Let's see, we have this that assumes, let's see, A4 is like we have 8.5 by 11 is common in the other side of the Atlantic. It's A4 is their common sheet. It's about similar in size. It's probably a similar stock as ours too. So they say 0.05 millimeters, possibly up to 0.1 millimeters thick. Let's see. Ooh, look at this. A piece of paper folded 103 times is as thick as the universe. We could check that claim later. How thick is printer paper? Science forums. Let's see what they have there. This person claims it's between 0.1 and 0.0254 millimeters. How did they figure this out? You would need some scientific equipment to measure this because a piece of paper is pretty darn thin. You would need something very special to measure it. Other thing is, have you ever seen anyone zoom in on a piece of paper? It's really rough. Even if as smooth as the paper feels to you, when you zoom in on it, it's wicked rough. What's that? And there's weaves going on. Yeah, there's all kinds of crazy stuff going on in there. What's this? Measurement, scientific. I saw a really cute site on it earlier when I was thinking about this. Where was it? Was it this one? I should have bookmarked it. That's not it. Science Alert. Have I gone there yet? No, but let's go there and see. Oh, no, that's not it either. All right, one more try and then I'm going to give up. How thick is a piece of copy paper? Did I click on that earlier? Maybe. Oh, no, I was already there. Okay, I lied. I'm going to try one more time. How about this one? Ah, here's one. Yeah, they have a special caliper that can be used to do super fine measurements. Okay? And what they'll do is they'll take a bunch of different measurements around the paper and then they'll average them. Okay? And so they're collecting data in that sense. They're taking a sample, because is the paper the same thickness everywhere? Well, no, it's not going to be. It's pretty hard to get something uniform everywhere. Right? But the measurements could be quite complicated. Like earlier we saw somebody wrote 0.0245, I think, millimeters thick. So just a related question here. So then we get into, well, what kind of paper is it, right? And then somebody said, okay, well, how about copy paper? Well, there's a lot of different kinds of copy paper too. So the ranges I saw for copy paper were somewhere between 1/10 of a millimeter. Remember what a millimeter is. So a centimeter is about the width of my little fingernail. You need 2.5 centimeters to make an inch roughly. A millimeter would be 1/10 of that, and then we want 1/10 of that. So here the claim a thick of paper is about 1/100th of the thickness, the width of my fingernail. And they range that all the way down to like 0.0. I saw something like, what I think it was like 243 millimeters. So one thing here is sometimes you have to have very special equipment. Yes, ma'am. Yes, yeah, they'll all be different thicknesses, and often they talk about the thickness of the paper by the weight, but weight doesn't necessarily go with thicker because some paper can be more dense than others. Like, do you ever use watercolor paper? Watercolor paper, if you put watercolors on it, it tends to spread just a little bit, so it's got some porosity to it, where other kinds of papers, the ink doesn't spread as much. Okay, so it kind of depends. So we have not only weight, but we have density of the paper, and that all leads to its thickness. But it's a complicated question. So what I'm getting at here is there's different kinds of data, there's different kinds of numbers, and you have to be careful when you ask a question. Okay, so we're going to go more into the kinds of numbers and the kinds of questions and how we go about collecting answers to those questions. All right, so back to data for a minute. So data types. The two main types of data are qualitative versus quantitative. Qualitative data is pretty straightforward. It's a quality, it's a name. Like green for eyes, like male for gender. It's the name of something, some characteristic. Quantitative is a bit more complicated. Even though there's types of different characteristics out there, quantitative can come in different ways. So for example, anyone ever seen a house being built? They make it out of sticks of wood. Often those sticks of woods are called 2x4s. However, if you measure a 2x4 in the United States, it is not actually 2 inches by 4 inches. Okay, it's more like 1.5 inches by 3.5 inches. It's rough cut at 2x4, but then they sand it down, and so it's smaller. So some things have what appears to be a quantitative label to them, but it's only a label. So we can label things with numbers. So an example is a 2x4 piece of wood. It is not actually 2 inches by 4 inches. That's just the name we give it. Sometimes you'll hear people in construction fields call it a nominal 2x4. Nominal means in name only. So you'll often hear for quantitative numbers that are labels, you'll also hear nominal. So that's one kind of quantitative data. You're using numbers, but they're only for a name. Anyone here seen their academic advisor recently because it's almost time to register again? And so when you go see your academic advisor, what's one thing they're going to want to know to help you figure stuff out? Well, they're going to want to know your student number. Okay. So my student number is something like 1185450. That's a number, right? So what? Like, would it make sense for me to take 10 away from my student number or to double my student number? To add my student number to yours? And like, why would you do that? So just because we have a number doesn't mean I can do math with the number. The number, it's a name only. Anybody have a social security number? Yeah, it's a name. It's another name for Gary Parker. Okay, so a lot of numbers are in name only. Other kinds of numbers. I have a roster. Okay, on that roster, I can't remember who's first. Ian's definitely not first. His last name starts with S. Let's see, your last name starts with L. Okay, Kaya, what's your last name again? I forgot. V. Oh, you're near the end. You're like last. Okay, so being last on my roster is different than like being last in a race. What if I sort it by first name? Well, she'll be in the middle maybe. Okay, so sometimes there's numbers and the only thing they mean is the order of something. So another kind of quantitative data we could get is ordinal. Okay, so example of that. Position in a list, or maybe getting first place for something. So it's another kind of way we use a number. With the nominal kinds of quantitative data, it doesn't make sense to add or subtract, do any math with those numbers. Does it make any sense to do any kind of math with ordinal numbers, like first place versus fifth place? Or is math useless there too? So there was a race and I got fifth place and Julia got first place. 5 minus 1 is 4. Could that have any useful interpretation? I was 4 places behind her. Yeah, so I can do some math on ordinal data. I can't do any math on nominal data. It's stupid because it's just a name. That would be like take the word Gary and add it to the word Ian. What? Doesn't make any sense, but it does make sense to maybe subtract two ordinal numbers, two positions, and say how many were in between them. Okay, so we can do some math here. So subtraction does make sense. For example, in terms of your position, yeah, position, it definitely matters, right? Does it make any difference that your student number comes before mine? Now they kind of hand it out randomly, so that doesn't matter. But it does matter whether you're the first person on the list and the last person on the list. Okay, well, there the only thing that matters, it means your last name came later in the alphabet. That's not important, but if we're talking about a race, it could be important. With ordinal numbers, 0 doesn't make sense though. There's no 0th place. There's no 0 position on a list. There's a first thing and there's a last thing and there's a bunch of places in between. Okay, and we only use counting numbers to get there. All right. Other kinds of numbers are called interval numbers. And interval numbers, you could subtract them, you could add them, you could multiply, and 0 finally starts to make sense. misspelled sense. Oh well. So for example, the time it took for something to happen. If it didn't happen, there will be no time. Having no time means it didn't happen. That's significant. Okay. Or maybe Julie and I were in the race and I took the same time as she took. We subtract those, we get 0, meaning it took us the same time. Okay, so 0 has some importance now. 0 didn't have any importance with ordinal numbers. It does have importance with interval numbers. Okay, so that's kind of interval. And then the last kind of number, I ran out of room here for quantitative, is what's called a ratio kind of number. Switch back to black. Quantitative data, or sorry, a ratio type. And so with a ratio type, 0 does, so we can do things like subtract, that makes sense. 0 makes sense with ratio numbers. And division also works and makes sense. Like suppose we were measuring heights. And I measured 68 inches in height. And once upon a time, I had a daughter who measured 34 inches in height. If we take my height and divide by hers, we would get 2, which means I'm twice as tall as she is. Okay. And so that comes up with the ratio kind. So again, there's 4 kinds of quantitative data. They are nominal, ordinal, interval, and ratio. And that's kind of the order of their complexity. Nominal, super simple. It's in name only. Ordinal, we're just putting things in order. Interval, 0 makes sense. Ratio, division makes sense. Sometimes it's hard to distinguish which one's which, like in the interval ratio part. If something's ratio, it's definitely interval. Ratio just has an extra characteristic to it. The reason that we kind of break quantitative numbers into these different components is certain kinds of statistical calculations don't make any sense for one type versus another. Like it makes total sense to say average these guys. Like maybe we measure blood pressure and we find the average blood pressure of students. Makes sense. If people ran a race and we found the average place, well, that's just the middle of the list. That doesn't mean anything. Okay, so it wouldn't make any sense to do an average on an ordinal number or to find the average value of a social security number. That's nonsense. Okay, so there's some kinds of things we can do with data that it depends on the type of data it is, whether we'll do it or not. And it's easy to mistakenly say, because you have numbers, you can always find an average. Oh yeah, but you can't interpret the answer. It doesn't mean anything when you try to do that. So that's going to come up as we're working with stuff. All right, so I'll give you some examples. We'll come back to that in a little bit. Let's get some more vocabulary out of the way. Play around with samples. Has anyone ever heard of a census? What context? Yeah, so the United States every 10 years does the US population census. And when we do a census, we're trying to sample the entire population. which is almost impossible to do, depending on the population. Like suppose I wanted to do a census on fish in the Umatilla River. Is that possible? That is impossible, right? We would have to drain the whole Umatilla River, put all the fish together, count them one at a time, right? So can you do a census? Yes, depending on the population, right? But you can't always do a census. But when we use the word census, we mean the whole population. Okay? So it's not just a word the United States uses when they do that. It's a generally received word in math, meaning everything in the population you're talking about. Otherwise, you have just a sample. And so a sample is just a subset of the population. So, for example, we have such an exciting time going on for this class because there's a presidential election happening. Let's see. Chance of president. Let's see. Chance of, let's go with Clinton winning presidency. Someone give me some data here. Probably not where I want to go. Time magazine. Okay, apparently I didn't type my query good. Oh, no. Let's see, what should I, oh, it's going to give me a stupid video. Go away. What should I type in? Sometimes I'm not good at Google searches. I'm trying to figure out like what's the percent of people voting for Hillary versus Trump. I could just type that. Clinton, what's that? Let's see. Top presidential poll, maybe. All right. Hillary Clinton leads Donald Trump, CNN 22. Okay, so here claim is Clinton has a 12-point lead over Donald Trump and has reached 50% support nationally among likely voters. Oh, go away, video. Sorry about that. Let's see. Current polls show where to go. Clinton with about 52, Trump with about 38, 5 for Libertarian, 2 for Green Party. So did anyone ask you when they get this data? They didn't ask me. Who they ask? How many people did they ask? Yeah, so let's see, a new ABC's new tracking poll, they have a link to it. This is a wonderful thing about online stuff. You can click, oh, look at this. I have this official looking document with a graph. Oh, this is awesome. Cool, check this out. Approval, disapproval, there's all kinds of cool data here.
Only you would get excited about a
Yeah, only me. There's lots of people like me out there. Oh, methodology. Oh, check this out. They're talking about how they collected the information. So this ABC News poll, this is important, was conducted by landline and cellular telephones. Okay, I've been getting lots of calls. If I don't recognize the number, I don't answer, but I did answer a couple of polls recently. Let's see, results have a margin of sampling error of 3.5 points. We'll take a look at that later, including the design effect, partisan divisions. Oh, 874 voters. How many likely voters are there in the US? Let's see, US likely voters, yeah. 874?
Oh, okay. I was about to say like.
How do you define likely voters? right, let's see. I find Gallup, I don't know if you ever heard of Gallup polls, super famous polling company. They always have great stuff with numbers in it. We'll look at them this week and next week a lot. Let's see. I want to know how many voters there are in the U.S. right now.
I got my ballots yesterday.
You did? I got mine a few days ago. I was so excited.
I cried.
You cried? Oh, I'm sorry. Okay, that's not what I
don't know what
want.
to do.
Let's see. How about what percent? I know. Let's search for percent. Could spell it.
It's kind of hard since half my family's Republican and the other half is Democrat.
I'm not typing my. Okay, let's see. How about
That's
this?
the thing, I don't want to vote.
Estimated turnout.
Like, I don't know.
Estimated turnout in 2008 was about 62% of registered voters. I want to know what percent of people in the U.S. are eligible voters. Oh, maybe that's what I should be searching for, eligible voters. Percent eligible. How do you spell eligible? Oops, apparently not like that. Percent of eligible voters.
What about you, Ian?
Voter turnout, voter turnout.
Yeah.
All right. So I'm going to offer a bonus to anybody who wants it. Find me an estimate of what percent of the U.S. population is eligible to vote. I'm going to write it down. Because I tried 3 times to search for it and I couldn't find it. So that means it's worth having you guys try and find it. What percent of the USA population is eligible to vote?
Man, if this was like back
Okay, a different.
wasn't voting, that would have been totally
So a different, but you guys are all whipping out your phones, all right. So a different but related question. Let's see, where's my pens? They are. New color. Would be what, I did totally word it wrong, yeah, because I wasn't getting what I wanted. Percent of US registered. So that's not the same thing as registered voters, because there's lots of people that are eligible to vote but never registered. And then another one that's related that we're going to take a look at soon, once you guys help me get some numbers, is the percent of voters who turn out. Right, so there's all different kinds of numbers, percent this, percent that, and it's a little tricky figuring out what percent we have of what.
I got 57.5%. John, is it correct?
57.5, I don't know the answer to it. So what you need to submit to me is a message somehow. I don't care how you message me through My Open Math or just email me directly. And I want your estimate with the place you found the estimate. So I can go in there, confirm, and see how good a source it is. And we'll talk about sources later.
Okay.
Yeah, so find something and then we'll see. That's okay. Make a note of it. Eventually send me a note before the next class. Send me an email with what you believe the percent is, where you found it, and then we'll talk about it in class. And anyone that has a good estimate with a good source, bonus for this unit, 10 points. Yeah, so that's why I was mentioning these other related questions, right? So voter turnout is different. Registered voters is different. Being eligible to vote, okay? So for example, people that are newly 18 have to register to be able to vote. And I remember being excited. I went and registered as soon as possible so I could vote. But there's some of my friends didn't. They waited years before they finally registered to vote. Okay.
I waited.
You waited a long time?
Oh, yeah.
Okay. Yeah. Yeah.
9% out of
In
how many
in current
people in the
polls,
population?
oh, okay. So people who are involved in the Democratic or Republican parties that nominated entire voter turnout, 9% of the voter turnout put Hillary and Clinton as the Democratic and Republican nominees. Cool. Everybody else, yeah, 9% of the population picked who the rest of the population gets to vote for.
What does that leave?
How many people didn't participate?
That didn't vote.
Okay, so, ooh, I have an idea. Check this out. So let's search for US population. And there's lots of sites that go over the US population. So right now, let's see, 2014, that was 2 years ago, we were at 320 million people in the US. Let's see, if I go to, where's a good site? US Census Population Clock. You found some more data? Ooh, save that site. That's a good one.
That makes me feel bad.
That's part of what we're looking for. So we're definitely going to need that link later. Okay. So if you could do me a huge favor, post that in our forum for this week, because we'll need that. Let's see, I want US population by age. Demography.
Gary likes graphs.
I love graphs. Graphs are great.
Yeah.
Oh, why can't I find what I want today? I'm having such a hard time searching. This week's forum. So that would be, so if you go to week 5, click on the collecting data questions forum and drop it in there. All right, and then one more lookup, and then I gotta get back to work here. Population distribution by age. Come on, show me a picture. Show me a picture. Data are loading. Ah, there's not a picture though. Darn. Okay. Ooh. All right, I will find a cool picture and get it to you guys later. Percent. Let's see. So United States, about 25% are children up to age 18. So that means 75% of the US population is over 18. So I'm missing those 18-year-olds. They're important, but it's a rough estimate anyway. So we could say a rough estimate would be, what are we at? We're at about 324 million right now. 1, 2, 3, 1, 2, 3. If we multiply that by 75%, then that means we've got 1, 2, 3, somewhere over 200,000 Americans should be eligible to vote. Over 200,000 should be eligible to vote. Okay, if the percents on this Kaiser Family Foundation site are accurate, and they claim that around 25% of people are 18 and under, so that means, and again, when you talk about 25% of a huge number like 320 million, there's a large margin of error going on there, right? What's 1% of 320 million, or a 0.5%? So 0.5%. Is he going to even do that? That's not right. Let's go 0.5. Even if those percentages were like 0.5% off, 0.5% of 324 million is 1.6 million people. That's a very large margin of error, agreed? Okay, so we got to be careful when we're throwing around percentages. But it turns out polls of about the size of 1,000, if they're well done, can give us reasonably accurate predictions of what the whole population is thinking or feeling or believing or going to do. Can you imagine that? 1,000 out of 320 million is enough people to be able to say, yes, we think it's 54% versus 38%. That's nuts. We'll talk more about that later. But that's a question we answer in a class that's totally devoted to statistics later on. How many people is enough to survey? Okay, back over here. All right, so you guys are going to send me some kind of note, either message me in my Open Math or send me an email if you think you have an answer to that question right there with the place you found the information. The more the merrier, right? Because we'll get a nice diverse information, all these great websites we can look at later. And you don't get extra credit. So find one. Look, yeah, it's no penalty. Just hope you find one. Post it by class on Wednesday, because we will use this in class to play around. All right, so that poll that we looked at just a minute ago, I think was from CNN. They said they had interviewed 874 people by phone or cell phone. And based on that, they're trying to make a presidential election prediction. Okay, so do you think it cost a fair amount of money for them to interview those 847 people? Okay, well, you have to somehow get that list of registered landlines. Somebody had to collect that information, so that costs money to get that. Then you have to pay people to talk to them. Before you talk to them, you have to very carefully script out what you're going to say. Because if we give somebody a vague question, then we set you off talking, are we all going to have a slightly different way of talking about it? Which means we're going to convey a slightly different message and not always have consistent answers. Right? So it turns out even talking to only 847. Now that sounds like a small amount when we're talking about the population of the United States, or maybe even the population of Oregon, or maybe even the population of like Hermiston or Pendleton. Right? Hermiston and Pendleton have like what, 16, 18,000 people? 800 out of that many? That's not that much. But let's think about it. Suppose the four of us set to this task. Do you think it would take us a while to talk to 847 people? It's going to take a while. Okay, so polling is expensive. It's expensive to set it up. It's expensive to do it. So that's why you want to minimize the amount of people you interview. However, would we pay any attention to a poll that says we interviewed 10 people? No. Hanging around Krabby's in Pendleton. Right? That makes it even worse, right? Where did you get these people? Okay, so when we do a poll, again, it is very costly. What we want to do is have some kind of random sampling going on. So we're going to talk a little about random sampling right now. I want something before class on Wednesday. Yes, for the extra credit. What about random sampling? Yeah, just a little bit. We still have some time. Like I'm done?
Yeah.
I'm not done. I'm just warming up. Yeah, okay, so random sampling. So we know what samples are. It's a subset of a population, okay? What does random mean? Yeah, random means random. No, we gotta do a better job than that. Okay, so unorganized. It's a good word. Unpredictable. Good one. Oops, wrong letter.
Different areas.
Different areas, different groups, unpredictable. Okay, so so the other day I was listening to some people talking, these young guys, and they were saying, "Hey, I went to this random bar the other day," and I'm thinking, you know, there was nothing random about it. You were in this area. You went to the bar. You didn't like throw a dart on a map and say, "Hey, let's go to the bar near this dart." Right? That would be more random. So sometimes we use random in the wrong way. Let's do a little experiment. I'd like you to pick. Let's see. I'll try to ask a good question. So the idea of a digit versus a number versus a numeral. A number is an idea. Like I can count to 5 on my fingers. I could write down the symbol for 5. That's a numeral. Sometimes numerals are big and they take multiple digits. When we write down numbers, we have 10 digits to choose from. A 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, 8, or a 9. We have 10 different digits we use when we write numbers down. So what I'd like you to do is randomly pick 2 digits right now. Okay, what do you got, Julia? What are your 2 random digits? 6, 8. Micaiah?
14.
Those are numbers, not digits. Digits are the single symbols, 0 through 9.
4.
Be random again. Come on, you can do it. It's hard to be random, isn't it? Okay, she's struggling to be random. Ian, did you struggle to be random also? 4 and 3. Okay, but you didn't want to say 4 because she said 4. Oh boy, that's not random at all, is it? Okay. I was thinking 0 and 1. Fan, you got any random digits for us?
9.
9. How about another one?
2 is missing.
So, Micaiah says 2 is missing. Okay, so anybody have a hard time being random? I did.
Well, now I did.
I said to you, digits are the things 0, 1, 2, up through 9, and then I tried to be random, and the first 2 digits I thought of were 0 and 1. The first 2 I read out when I was talking about what is a digit. So I biased myself, and I couldn't stop thinking about them. That ever happened to you? You can't stop thinking about something? Get stuck in your head? Computers try to be random. Anyone got a smartphone here? Type search for random number on your smartphone or computer or. So this should be easier than searching for the other stuff we were doing. Oh, I didn't want to search for generator. I just wanted a random number. And if we're all going to Google, we'll probably all get similar results. I got taken to, let's see, random.org, true random number service. Okay. And the thing, oh, true random number generator starting at 1. I wonder if it'll let me start at 0 and go through 9. Generate. I got a 9. I got a 0. I got a 5. All right. So off to the side here. Oops, I lost it. Come here. There you are. My random number generator from random.org. They have a pretty cool website. I like it. It turns out being random is rather difficult. It's not easy. And it's a mathematical problem people have been studying since computers were invented and before that. Okay. Sometimes we'll draw cards to try and be random. Sometimes we'll roll dice or flip a coin. Okay. So we want some act of nature to be involved in the randomness so we can believe that it's random. It turns out I've collected random digits from people before. People are very unlikely to pick 0 as a random digit. Doesn't sound random enough. Yeah. 7 is a pretty common one, yes, yeah. So if you look at a distribution of digits where people are trying to be random, bottom line, if something's random, each thing has the same chance of being picked. And so if you do it often enough, what you'll find is you'll have the same number of zeros, same number of ones, roughly the same number of twos, and so on. So I'm just going to demo that in a spreadsheet quick, just to get the idea of randomness home. Oops. Let's see, I'd started a spreadsheet here. And so it turns out there's a way to tell the computer to be random. One way is to do what's called rand. And let's blow this up. And if you just type rand and open and close the parentheses, it will pick some random number between 0 and 1. It could pick 0, but it won't pick 1. And it's going to have a whole bunch of decimal places. So all spreadsheets have a random number calculator that gives you some, you could consider a percentage, a proper percentage. And if I do something else on the screen, like type a 6 and hit enter, it'll regenerate that random number. And in some spreadsheets like Excel, if you type F9 over and over again, it'll regenerate the randomness again. I can't remember if Google has a regenerator key. The other way to do random stuff on a computer is to use the rand between function, which is what that website Ian and I were at does. Says, okay, what's the lowest number you want? 0. What's the highest number you want? 10. And it only picks integers, which are like 1, 2, 3, 0, -1, -2, -3. And it includes the endpoints. It could pick 0, it could pick 10. And then what I can do is I could fill that down a whole bunch of times. And so it's just going to randomly generate digits 0 through 9. And maybe I'll do 500 of them. Okay, so there's 500 of them. If it's truly random, then I should have about as many zeros as 10s, as 3s, as 5s, and so on. So now that they're highlighted, I could say, hey, computer, can you count those for me? And it turns out Sheets has a really quick way of counting similar stuff. So I hit chart. It says, hey, would you like me to keep track of the 0s, 1s, 2s, 3s up through your 9s there? Or, oh, I had 10s. I only meant to go through 9. I messed it up. Oops. Are these all the same height? No, I only have 500. So the question is, how many do you have to do before it starts to even out? Like, consider flipping a coin 500 times. About how many heads would you expect to get? Yeah, it's like, isn't it 50-50 for flipping a coin? So shouldn't we expect to get about as many heads as tails? Will we get exactly the same number of heads and tails? No, not exactly. If you're bored tonight, try it. Flip a coin over and over, count every time. You'll get close after a while, but sometimes you could be way off. Like you could get 10 heads in a row. That's totally possible. It's not likely, but it's possible. So I'm gonna, yep. Yes. Yep. Like jury duty is supposed to be random. I got selected multiple times in 1 year, and I got selected for every jury there is to do in the region within like a 3-year span. And I haven't been selected in the last 10. I was like, what the heck's going on?
Doesn't it have to do with
I don't, on a jury, no. So one cool thing about this is as I change the spreadsheet, it'll regenerate the randomness. Now look at, they're almost all the same height. Okay, so with respect to randomness, there's the idea that if you do something enough times, you'll see things even out. The question is, what does enough mean? Well, it could be 1 million, it might be more, before you things really even out. I only did 500, it's not a lot. Okay. So something would be random if I randomly selected a person in this class. There are, say, 10 people in the class. That means you each have a 1/10 chance of being picked. You're all just as likely to be picked as the next person. Okay? So like the random testing of individuals at an employment place. Every single person should have the same exact chance of being selected as anyone else. Even if you got selected yesterday, there's the same chance you'll get selected tomorrow or whenever the next testing is. Okay, that's what random means. So somebody could be selected 5 months in a row if it's monthly testing. It can happen. It's unlikely to happen. It means you should investigate the testing, the random person generator. Yeah, and then generally they're using like techniques that we're going to talk about in terms of how do you generate somebody randomly. So let's get back. So being random is very challenging. Okay. So let's just make a note. It is hard to be random. but randomness involves things being equally likely. Oops, extra letter. Equally likely means we have the same chance. Each thing has the same chance. There we go. So the bottom line for a random sample, it means each thing that could be selected has the same chance of being selected as every other thing, whether that thing's a person or an animal or a pen, doesn't matter. Same chance. So a related idea that you'll hear a lot in sampling is the idea of a simple random sample. And then I'm about out of time for talking about this stuff. We'll pick it up next time. So a simple random sample okay. So maybe we need samples of size 10. So for example, let's take a sample size of 10. Sample size could be 874, like that CNN poll. To be a simple random sample, then every possible sample of size 10 has the same chance of being selected. Okay. So suppose we're doing some kind of drug testing at a workplace and we're supposed to select one person a week to be tested. That would be just a random sample, not a system random sample, because I'm just picking one person at a time, as long as I can ensure that that person has the same chance of being selected as any other person. Like maybe we put all their names in a hat and you reach into the hat. Okay. Or we have a list of people on a spreadsheet and we use the random spreadsheet. Okay. So suppose, for example, we were in a situation like that. We could go to our spreadsheet over here and we could say, let's see, equals rand between, and we have the first person on the list, and maybe our organization has 123 people. So if I do the rand between 1 and 123, that will pick a person in my list at random out of 123 people. Person number 123 is getting tested today. Okay. So that's the idea of a random sample. A simple random sample is when we're always looking for a group of 10 people or a group of 5 people. And then I have to ensure that any particular group of 5 has the same chance of being picked as any other. Okay. Like right now, there are 5 of us actively working on Math 105 at BMCC. Okay. So we, like, suppose the college wanted a survey for something about the way the bond construction is going. And they were only looking for samples of 5 people. We are one likely group of 5 people that could be selected. Okay. But it could be people that have nothing in common in terms of their classes. But it could be they have everything in common. But it wouldn't matter. If they were looking for 5 people, our group of 5 people should be just as likely to be selected as any other group of 5 people possible. Okay. So once you're talking about a group of people being selected and you're talking about random, then you're looking at what's called a simple random sample. And I know I said I'd shut up after this definition, but I decided I have one more I got to sneak in, and then I will shut up, I swear. The idea of what's called a convenience sample. So I happen to be on the bond oversight committee. And suppose they tasked me, because I'm a math teacher, with doing a random sample of 5 people. And I said, hey, I just found a random sample of 5 people. Us. There's 5 of us. We're related to BMCC. This is not random at all. We are all here for a reason. It is convenient for me to grab the 5 of you because you're right here, or 5 of us. I'm including myself. So that's dangerous. Convenient samples can totally mess stuff up. Because when you grab things that are convenient, they generally have something in common and will bias the results. So when we start wandering away from the idea of a random sample, then we have bias to worry about. Means we're somehow, with our methods, we're swaying the data away from where it naturally would be if it was a random sample. So we don't want to introduce sampling bias. A convenient sample is one way to do so. So over the next couple of days, we're going to talk more about what's a statistic and what's not, the kinds of things we can take statistics on, the ways we can go about sampling, and what kinds of biases we can end up with. Yep. If the HR department was doing the random sample, and there could be some bias. Convenience means you're grabbing the sample because it was easy to get, is what convenience generally means. So here's an example of a convenience sample. A group of statistics students I worked with before were curious about what % of the population had diabetes. And they did some sampling, and they found, based on their sample, like 30% of the population had diabetes. Like, that seems too high to me. Where did you get your data? And everyone said, oh, mostly Sheila collected the data. Where'd Sheila collect the data? Sheila works at a doctor's office, and she asked people that came in to see the doctor. Oh, come on. If you have diabetes, you have health issues, right? If you have health issues, you're going to go see the doctor. So there was not. So she introduced bias because she grabbed people that were convenient to her coming to the doctor's office, which totally made their survey useless. There was no data that we could rely on there because it was too biased toward people who were sick. And turns out diabetes is one way to get sick and have other problems. So we'll talk more about that over the next couple of days. So please, this chapter is important for reading. There's less math in this chapter than any other chapter. It's more definitions. And so we're going to be going over those definitions and playing around with different situations. All right, that's it for today. If you didn't finish your written assignment for finance, please get busy. I'm going to be hanging around for a little while if anyone needs tips or help on that. Otherwise, I will start grading those tonight. How you doing, Fen?
I'm good.
Okay.
I was a little confused